Let's look more at entropy and microstates, and let's visualize the relationship between the two. So let's consider an example where we have two particles distributed by two boxes. And I've shown the particles here as a red and blue circle and the two boxes as two squares side by side. So we want to look at what are all the possible combinations or distributions can these two particles distribute between these two boxes? What are all the possible ways these two particles can distribute between these two boxes? So this is the first way, right? Both particles can be in the left-hand box. The other possible way is where both particles are in the right-hand box and they're not in the left-hand box. And then they can both be one in the left-hand box, one in the other, and then we can flip them, right? Where in this case, the red was in the left, but now the red is only in the right and the blue is in the left. So we got four possible ways that these two particles can be between the two boxes, right? This is the number of microstates. This is the number of microstates, which is four. Four different ways that we can distribute these two particles between the two boxes. And if you use the formula, right, W equals 2 boxes squared, because we have two particles, we'd also get 4. Let's look at another example. Consider four particles distributed by two boxes. So if we visualize this, right, we can have all four particles in our left-hand box and nothing in the right-hand box. And then we can have the opposite, where all four are in the right-hand box and nothing in the left-hand box. We could also have 3 in the left-hand box and 1 in the right-hand box. And these are basically 4 different ways that we could have this distribution of 3 in the left-hand box and 1 in the right-hand box. So there's 4 different ways we can have this 3 in the left, 1 in the right. Right? And then if we flip it, where we have 3 in the right-hand box and 1 in the left-hand box, and there are also 4 different combinations of this distribution. Then lastly, we could have them spread evenly, where we have 2 in the right-hand box, 2 in the left-hand box. And these are all the possible ways, right? There's 1, 2, 3, 4, 5, 6 different ways we can have an even distribution between the two boxes. So each of these ways in which they have the same distribution, right, or the same arrangement between the two boxes are called distributions. So microstates with equivalent particle arrangements, right? Equivalent particle arrangements, meaning in this example here, each of these have 3 in the left and 1 in the right. So that would be what we consider an equivalent particle arrangement. They're grouped together, and in this grouping, we call this grouping a distribution. So we have 5 distributions here. 5 distributions here. Now, for determining our microstates, right, we want to ask the question, which distribution is the most likely? Which one is the most likely, right? Because we have 5 distributions, and essentially 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus 6. We have 16 different microstates, right? 16 different ways we can distribute these 4 particles between the two boxes. Which distribution is most likely? And the one that's most likely is the one that has the largest number of microstates, right? Because the largest number of microstates is the one of greatest entropy. It's the one of greatest entropy. So the one that results in the greatest entropy is the distribution that's most likely, which in this case is our even distribution, right? It's our even distribution, which, remember, we talked about that before when we first introduced entropy. A uniform distribution is most likely, and we see why mathematically, because it results in the highest entropy. So I'm going to pause here